You have seen in the last class that what is the structure of a diode? Okay. Like this. We saw that how does a diode look like under no bias condition. So there are two sections of the in a diode. There's a P section and an N section. We call it as a P region and the N region. So on the P side, we are having the holes as the majority carrier. Okay, we have also seen what are majority carrier, what are minority carrier. Okay, so in the N-type region, we are having electrons as the majority carrier. Then you have seen that there are certain immobile ions present in the both the regions, and in between these two sections, that is the P and the N section or the N region, there is a junction, and this junction is called as the depletion region because here we don't have any mobile charges. There are charges, but these are all ions. They cannot move. So due to the presence of these ions, what happens? A barrier is created, a potential barrier is created, and due to this barrier, you don't find any movement of the majority holes from the P side into the N side, or the movement of electrons from the N side into the P side. Okay. Below in the figure B, you can see the symbol of the diode, that how we represent a diode in our copies. Okay. Whenever we represent a diode in our copy, we write it, we show it with this symbol, a triangle symbol. Okay. And obviously we have seen what is a majority carrier, what is a minority carrier. Then you have also seen that what happens if we apply a bias to a diode. So there are three figures in front of you. First is the no bias condition. Then there was a forward biasing condition, the second figure, and there is a third figure, which is the reverse biasing condition. And biasing means, as I said, that whenever you say biasing, it means you want to make the diode to work in a certain region. Okay. So when you're forward biasing, okay, when you're forward biasing, you are applying the positive terminal of the power supply. Okay, the positive terminal of the power supply, this one, to the anode of the diode. This is the anode of the diode. PP, call it as a PP. Okay. But when you are reverse biasing, you are applying the anode of the diode, you are applying the negative terminal of the power supply. In fact, you are connecting the negative terminal of the power supply to the anode of the diode. So here it is a PN connection. So it's a positive with N. So we remember it like this, PP, PN. Okay. Then you saw that what happens when you are applying a bias and what is its effect on the barrier, the potential barrier. So here, as you can see in this figure, that the red colored curve represents V naught. It is called represented by V naught. Okay. So if you look at this red colored curve, it is like this. Okay. And this is the barrier that is existing under no bias condition. Okay. Under no bias condition. It is represented by V naught, okay, also known as the potential barrier, also known as, this is also known as the contact potential also. Contact potential. These are the various names. So under no bias condition, there is a barrier that is existing which does not allow the holes on the p side to go into the n side. And similarly, such a barrier also exists for the electrons which want to move from the n side into the p side. So when you forward bias a diode by a potential Vd, then you are actually reducing this barrier by Vd. Okay, so this is represented by V naught minus Vd as it is written here. With this blue colored curve, as you can see, it is the reduced barrier. You can see that the barrier has reduced. Now, when you reduce the barrier, then these majority charges can now easily cross into the n region and vice versa. So the holes from P can go into the n side, the electrons from the n side can go into the p side. So when you keep on increasing the forward biasing, you are actually reducing this barrier. So that's why you see that there is an increase in current through the circuit whenever you are forward biasing the diode. But the opposite, if you look at into the reverse biasing, when you are reverse biasing by a value of Vd, and as you can see in this figure, that this is V naught plus Vd, the yellow curve, as you can see. So this is, as you can call this as Vd. Okay, this is Vd. So you're adding actually there is a barrier which is already existing under no bias condition, but you are increasing that barrier. You're increasing that barrier by applying the reverse bias. But at the same time, what happens is that when you increase this barrier, this actually means that for opposite charges, for the minority charges that are existing in the p or the n region, this is actually assisting their movement. So when you reverse bias the diode, then also a small current would flow, okay, and that current is due to the minority charges. So if you know what is biasing, what is forward biasing, what is reverse biasing, okay, then you can easily look at the current versus voltage characteristic of a diode. Okay. So our circuit is like this. Okay. Normally, when we conduct an experiment in the lab, it is like this. You are going to apply a resistor over here, and this is the potential that is applied externally. And as you can see, it's a forward bias case where you are connecting the positive of the power supply to the anode of the diode. So to perform this experiment, what you do is you connect a voltmeter. Okay, and this is connected in parallel with this diode to measure the voltage across the diode. And you also connect an ammeter. Okay, also connect an ammeter to measure the current in the diode, and this is actually measuring ID, the diode current. This is ID. Okay. So on the y-axis, we put the diode current ID. On the x-axis, we are employing VD. All of you are connected? You are able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Oh, okay.
Yes, sir.
Okay. So,
Yes, sir.
yeah, fine. So there are two regions. One is the forward bias region, and there is a second region is the reverse bias region in the characteristic of a diode. So to plot the characteristic, we are having two axes. On the x-axis, we are having VD, the voltage across the diode, and on the y-axis, we are having the current. It is the current through the diode. So under forward bias condition, the voltage across the diode, when you measure it, it is going to have this polarity. That is, it is going to be positive in nature. It will be having a positive value. So like here, if you say it's a zero point 0.1 volt, 0.2 volt, 0.3, 0.4, 0.5, 0.6, 0.7, like this. Okay. So when you plot the characteristic, okay, so for a particular value of VD, you make a table in the lab. You make a table like this, VD and ID. So you first of all look for what is the current when the VD is 0.1 volt. You will get some current which is in microamperes. Okay, not much. Then we look increasing this to 0.2. You say that okay, I get 0.1 milliampere. Then 0.3 is again measure, it is 0.2 milliampere. So like that you keep on increasing. Okay. So then what you do is you plot a characteristic by through this table. So initially the current is very small. So and this on the positive y-axis, this is in milliamperes. You keep the scale in milliamperes. So what you do then is you plot it, and when you plot it, okay, so you plot this point. So initially the current is very small. So you say that okay, this at point 1 I'm having this point. At point 2 the current has increased by a small value. At point 3 it has further increased. At point 4 it is increasing. At point 5 it goes like this. And at point 6 it goes like this. At point 7 you're somewhere here. Okay. So this way you get these points from this table. And you connect all these points. You connect all these points. So when you connect all these points with a free hand, get a exponential kind of a characteristic like this. Okay. So in this way, you get your characteristic in the forward bias region. Okay. This is the characteristic in the forward bias region. And here the current is in milliamperes. Like here, you can say that this is 0.5 milliampere, this is 1 milliampere, then it becomes 1.5, 2, 2.5, like this it will go, and here it will, you can find here as somewhere around 10 milliamperes, like that you will be having. The same thing when you do for a reverse bias condition. Okay, when you do it for the reverse bias condition, okay, in the reverse bias condition, your current is going to be very small. So here the voltages are also increasing quite significantly. So here your first voltage is supposed 2 volt. Okay, you represent it as a 2 volt, and here it is 4. If I put a sign also, because it's a negative voltage, because in reverse bias condition the circuit will look like this. The power supply is negative, is connected to the anode of the diode. So you're going to connect a multimeter over here. Okay. Here a voltmeter, suppose. So this is for measuring VD, and here you are going to connect an ammeter for measuring ID. So this is going to give your ID. Not the direction will be opposite. Okay. The direction of the arrow will be opposite because it will follow the direction of the power supply. So now if you look at the reading, now this is positive and this is negative. Okay, because this is connected to the negative terminal of the power supply. That's why you get a negative voltage over here. So -4, -6, -8, -10, like that. It's 12 like this. So when you do this thing, you get a table. You get a table like this. So you increase the voltage across the diode to 2 volt. You measure the diode current. So you get a certain point. Suppose you get a point over here. Then you increase it to -4, and there is not much significant. There's not a significant rise in current. Uh, and also in the reverse bias condition, your scale is going to be in microamperes. You have to remember this. Otherwise, you will not get a correct plot when you are plotting a graph. So when you increase it to -6, again there is a small increase in the current. Okay, you get these points like this. -8, a small increase. -10, a small increase. -12, again a small increase. So when you connect all these points, okay, when you connect all these points, then with a free hand again, so you get it like this. You get a characteristic like this, which looks quite straight, and which looks in most of the books, if you look at it, it will be quite parallel to the x-axis, the negative x-axis. Okay. So normally, the diodes that we use in the lab, okay, they are known as the rectifier diodes. They're called as rectifier diodes. And their breakdown voltages are up to 50 volts. Okay, 50 volt breakdown voltage. So whenever I say breakdown, it means it's obviously you're going to put a negative sign. I'm going to talk about a negative voltage, but since it's a magnitude that I'm specifying, so I'm saying 50. The 50 volt breakdown means I'm talking about a negative voltage across the diode, which can go up to 50. Okay. So usually in the labs, we are going, whenever we perform this experiment, we are having a diode, okay, which is having a breakdown of 50 volt. So you don't, with the available power supplies in the lab, okay, whose maximum value is 30 volt, whose maximum value is 30 volt, it means you can give a maximum of -30 volt across the diode. In that case, you never find a breakdown in our lab using these diodes. So you get a line like this, and so you stop somewhere here. You say that, okay, this is our characteristic. Okay. So this is the characteristic in the reverse bias condition. Now, I hope, are there any questions here? No questions? Okay. Okay. So I'm going to do, what I'm going to do is I'm going to redraw this. Okay. Because what I've done now is that it was plotting it, but now I'm not going to plot it. I'm just going to draw it. This is your characteristic in the forward bias, and this is your characteristic in the reverse bias. It goes ideally like this. Okay, like this. Okay, on the y-axis is ID, on the x-axis is VD. Okay, so this is the forward bias region. This is the reverse bias region. So what you see is exponential characteristic in the forward bias region, and in the reverse bias, the current is nearly constant. So theoretically, if you go, it is somewhere it becomes like this. It becomes like this. So this is a constant. It becomes nearly constant because you don't have many charges to increase the current. So this is called as represented by I naught, and this I naught is known as what it is called. You all have studied diodes. What is this I naught? What it is called?
The photocurrent.
Hmm?
The
Photocurrent.
drift current.
Drift current? No.
It's a photocurrent.
What? Please, I can't hear
Photocurrent.
you. What current? Can you repeat what it is called? This is known as the reverse saturation current. Okay, reverse saturation current. Okay. Now, why it is called saturation? Because its value is getting fixed. Somewhere it increases, but later on it becomes nearly constant. Okay, and it becomes nearly constant until you reach a breakdown region. Okay, so this is the saturation. This is called a reverse saturation current. So, as the name suggests, this current is flowing in the reverse direction. So, whenever we look at a diode, okay, this is the direction of the forward current of a diode. Whenever a diode is forward biased, this is the direction of the current. And whenever the diode is reverse biased, this is the direction of the current. Okay, it's a reverse current. It is moving in the reverse of the forward current, and that's why we call it reverse saturation, reverse current. And why saturation? Because its magnitude is getting fixed. It cannot increase further. Okay, its magnitude is getting fixed, and it's called a reverse saturation current. So what happens if you keep on increasing? So as I said, in the lab, we don't come across this breakdown condition, but when you keep on increasing, and suppose theoretically, if you reach a 50-volt breakdown, then what you see is that at this point, the current increases drastically. In this case, the current is increasing, but the voltage across the diode is nearly fixed. It is not changing. So the current is increasing. So with the case of a rectifier diode, as I had specified, this diode would get damaged. It will get damaged if it goes into the breakdown region. So rectifier diodes are not designed to work in the breakdown region. But at the same time, you might have heard about Zener diode. Have you heard of Zener diode?
Yes,
Yes.
sir. Yes, sir.
Yes. So Zener diodes are designed to work in the breakdown region only. So these have various values of breakdown regions. They don't typically have this so high breakdown. They may have a breakdown of minus 5 volt, okay, 9 volts, okay, 12 volts, like this. So these diodes, Zener diodes, they will reach the breakdown region very early. So in the forward bias, these Zener diodes have the same characteristic as a normal diode. In the reverse bias, also you find the similar characteristic, but only you find the difference is that you get a breakdown region quite early. So you get breakdowns at 5 volt or 9 volt or 12 volt, like that. Okay, so we'll be covering this thing later, that what is a Zener diode and how it is used. Okay, so but in the case of a rectifier diode, we don't bring the rectifier diode over here in the breakdown, because it will just damage the diode. The diode will get burnt. Okay, so you don't use this rectifier diodes in this region. So
So,
हाँ बोलिए.
so in rectifier diodes, a breakdown region for forward bias is very early in comparison to reverse bias.
No. It's not called breakdown. In the rectifier diode, it is not, this is not called breakdown. This is not breakdown. Okay. So there is a term called as cut-in voltage. Okay, cut-in voltage. In your experiment also, when you perform this experiment in the lab, you are asked to suppose find out what is the cut-in voltage. So what you do is you take a scale and you draw a tangent like this, tangent to this characteristic. Okay, you like draw like this. It goes like this. Draw a straight line. Yeah. Somewhere here, this is your cut-in voltage. Okay, this is not breakdown. This is called cut-in. Okay, breakdown is different from cut-in. When you say cut-in, means you're saying that after this voltage, the diode is conducting significantly. Okay, and below cut-in, the diode resistance is high even in the forward bias region. So the breakdown term is used in the reverse bias only. It is not used in the forward bias. So the term that is used in the forward bias is called, this is called cut-in voltage. Cut-in voltage of a diode. For silicon, this voltage is around 0.5 to zero point 0.6 volts. Okay. So theoretically, in some books you will find 0.5. For germanium, this is 0.2 or zero point 0.3 volts. Okay. So practically, when you conduct such an experiment, because in our lab there is a silicon diode only. So when you conduct such experiments, you can find the cut-in. You first of all plot this from this table. You plot this characteristic from the table, and when you are asked to find the cut-in, either you can look into the readings, like you can see that at 0.3 it is zero point 0.2 milliampere, but when you keep on increasing, then you will find a value of VD which is around suppose 0.55 volt, at which the current is becoming significantly high, that it is directly jumps to 2.5 milliampere, like that. Okay. So before this, it is just at 0.5 volt. This will be just suppose 0.35 milliampere, like this. But at 0.55, it will significantly jump. So it will suddenly jump to 2.5 milliampere. So you say from the table, you can say that this is the cut-in voltage. But since the readings in the table are discrete, you don't have a continuous readings present over here. So this may not give you a correct value. So what you do is you go back to your characteristic and you draw a straight line using a scale, draw a tangent kind of a line, and wherever this line is going to meet the x-axis, that is considered as cut-in, and then you compare this value with the value that you obtain from the table to get to understand that what is the typical voltage, because even this is not going to give you an accurate value of the cut-in voltage. Okay, but it will give you a rough idea that okay, if I am between 0.5 to 0.6, then I am going to get a cut-in. So in that way, you can say that this is the cut-in voltage.
Yes, sir.
Okay, so we use the term cut-in voltage to represent the voltage beyond which, okay, voltage beyond which the diode is going to conduct significantly. Okay, below that, the diode is considered to be nearly off. Okay, so this is a characteristic which is we call as a accurate characteristic, or the characteristic which is obtained using this experimental from the experiment. Okay, so this is a very accurate characteristic. And this characteristic, if I go here, then this characteristic is represented by an equation. So the diode equation, diode current equation, ID, you might be all aware of it. Anybody remembers what is the diode current equation?
So it is I, the sum of diffusion current and drift current.
This is a new term that you are using. I hope everybody knows what is a diffusion current and a drift current. Yeah. I'm talking about the equation. Okay, so have you seen this equation? ID equal to I naught e raised to Vd upon eta Vt minus 1. Have you seen this equation?
Yes, sir.
Where eta is called a constant, it is 2 for silicon diodes, and it is 1 for germanium diode. Okay. This Vt is capital T, that is the temperature in Kelvin, upon 11600. And whatever you get here, it is called the volt equivalent of temperature, and this many volts you say. Okay, whatever value you get here, this is having a unit of volt. Okay. So this is called as the diode equation, diode current equation. Okay, a very important equation. This is called the diode current equation. Okay. This VT, this VT is called the volt equivalent of temperature. Okay. Capital T here is in Kelvin. Okay, is it capital T is the temperature in Kelvin. So if I say that that we are at, if capital T is 300 degree Kelvin, okay, if I say that capital T is 300 degree Kelvin, then VT, if you can calculate, you can use your calculator, then VT will be 300 upon 11600. How much it is? What is the value of this VT?
Sir,
Anybody?
0.0258.
0.0258 or 6. So how much it is? 256 or 258?
So 0.0258.
8 volt. Okay. This is
Yes.
0.0258 volt, and this is called as 25.8 millivolts. Okay. So, and the third term, which is here, is the VD. As you know, VD is the voltage across the diode. Voltage across diode. So it is positive. It is positive when forward biased, when the diode is forward biased. So if you say that diode is forward biased by 0.5 volt, so you will put, or you will substitute plus 0.5 over here in this equation. But if it is, you know that it's a reverse bias, then you put a negative sign. Okay. So this VD is negative. Okay. It's negative in the reverse bias condition. It is positive in the forward bias condition. Eta is a constant. It is 2 for silicon, 1 for germanium. And this VT is actually having another expression, which is KT by Q, where K is called the Boltzmann's constant. Is the Boltzmann's constant. Q is the charge of an electron. Capital T is the temperature. So when you substitute for K and Q, you end up with this equation. And we use this equation normally while doing any calculation. And the another term that is in this equation is the reverse saturation current, as you had already seen here. Okay. So this equation, okay, diode equation will represent your characteristic. Okay, it's an exponential characteristic, as you can see here. If you substitute for all these values of VD and find ID, then you will get nearly this kind of a plot over here. Okay, an exponential plot. So for various values of VD, you will get various values of ID. You just put plot all this over here. So when you connect these things, you get this kind of an exponential characteristic. So this is called the accurate characteristic of a diode. This is called the accurate characteristic of a diode. And this equation is valid for both the forward bias as well as the reverse bias condition. Okay, this equation is valid for both the forward bias as well as the reverse bias condition. So suppose I say that this I equal to I naught e raised to Vd upon eta Vt minus 1. I say that suppose Vd is minus 50 volt, as we have said. It is minus 50 volt, or suppose minus 20 volt, suppose minus 20 volt. Then you substitute it here, then what you get is I equal to, this implies I equal to I naught e raised to minus 20 upon eta. Suppose it's a silicon, suppose it's germanium diode. For germanium it is 1. Vt, suppose it's a room temperature, it is 0.0258 minus 1. Okay. So what happens is that this term is going to be, it's having a reverse power, negative power. So this term, when you solve for it, it will be very negligible as compared to this 1 over here. Okay, it will be very negligible as compared to this 1. In that case, you say that I is approximately equal to minus I naught. Okay, I or ID, whatever we are putting, ID, the drain current and the diode current. ID is equal to minus I naught. What does it mean? It means that you are saying that this is a diode, and under the reverse bias of minus 20 volt and the reverse bias of 20 volts, the current through the diode is the reverse saturation current. And in the form of an equation, when you put a negative sign, it means you are saying that its direction is opposite to the direction of the forward current of a diode. So whenever you solve any numerical, any problem using this equation, then if you have a negative sign along with your answer, it means you are working in the reverse bias region, and whatever answer you are getting, it is actually the negative sign is showing that it is opposite to the direction of the forward current. So don't worry if you are having a negative sign in your answer under reverse bias condition. It only means that the direction of the current is opposite to that of the forward current. So if this is the forward current, I will use a big arrow for the forward current, because the forward current is going to be always larger than the reverse current. So this is the direction of the forward current, the yellow line, and this is the direction of the reverse current. So this is a very important equation that we will be using for solving many of the uh, problems. Okay. And this equation is, I'm repeating, it is valid for a practical kind of a diode. It is going to give you an accurate or nearly accurate. It's going to give you a nearly accurate representation of the diode characteristic. Okay. Any questions?
No, sir.
Okay, so with this, now I will go back to the slide, and then you can see that this already we have seen that. Then you've already seen what is the reverse bias and how the depletion width. Okay, you can see the depletion width increases when you are the reverse bias condition. And when you are under the forward bias condition, the depletion region is quite narrow. Okay, the depletion width reduces. Now this is the equation that I had just discussed. The Boltzmann's constant, its value is 1.38 into 10 raised to minus 23 joule per degree Kelvin. So whenever we want to find the temperature in Kelvin, what we do? Either if you know the temperature in centigrade, you add 273 to it to get the temperature in Kelvin. So the equation that we use for Vt normally is capital T upon 11600. We remember this equation because we don't always put the Boltzmann's constant, the charge Q, to find this value of Vt. Now, this is exactly the Vi characteristic of a diode. Okay, Vi means the voltage versus current characteristic of a diode. So here you can see that how the current is varying. Okay, there are two diodes. I think one, the hashed one, the dashed one is the germanium diode, and the other one is the silicon diode. because the cut-in voltages, as you can see, they are different. Then we have also seen what is a breakdown region. So as you can see, the saturation current, if you can look at this figure, you see that the saturation current is nearly a straight line. Okay, it's a nearly a straight line which is running parallel to the x-axis until it reaches the breakdown region. So we say that the saturation current is nearly constant at a given temperature. Okay, the temperature is an important parameter. So whenever I say that a saturation current is constant, then you must always ask that what is the temperature. Because if you change the temperature, then the saturation current will also change. Any reason why? Any reason why the saturation current is going to change if the temperature is changing?
Sir, it will affect the flow of electrons. The
Yeah,
temperature change.
as you know that yesterday also you have said that if we increase the temperature, the conductivity increases. Okay, the conductivity of a semiconductor is going to increase. So when you are increasing the temperature, so suppose you are at a 300 degree Kelvin, then there are a certain number of electrons and holes which are free. Okay, but when you increase the temperature to 400 degree Kelvin, then you are having more number of holes and electrons available. So it means you are actually, your reverse saturation current is going to increase with the increase in temperature, because this current is due to the minority charges, not due to the majority charges. So if temperature increases, the charges increase. These charges that are increasing due to temperature, they are not dependent on the doping. Okay, they're not dependent upon the doping that you have done. So this is a comparison of the three kinds of semiconductor materials. One is germanium, which is very common, and silicon. These two are very common. The third one is a compound. It's a gallium arsenide. It's a gallium arsenide. Okay, its cut-in voltage is around 1.2 volt, as it's visible from this figure. For a germanium diode, the cut-in is 0.3. For silicon, it is 0.7, and it's quite visible. You can see it from this figure itself, that how the characteristics are varying. Okay. For the three materials, germanium, silicon, and gallium arsenide. Okay. You may also look at the reverse current. Okay, so the germanium is having the highest reverse saturation current. Silicon is having a lower reverse saturation current as compared to germanium, whereas gallium arsenide is having the lowest reverse saturation current. Okay. So then there is an effect of temperature on the characteristic of a diode. So the blue colored line, as you can see, this is the characteristic at 25 degrees centigrade. And if you look at the left hand side, there is a characteristic at 125 degrees centigrade. So if the characteristic is moving towards the left hand side, that is towards the y-axis, it means more current you are getting at a lesser voltage. Okay. You are getting a more amount of current at a lower value of the diode voltage. So whenever the characteristic is shifting towards the left hand side, it means the current is increasing. And whenever the characteristic goes towards the right hand side, that is, if you look at the minus 75 degrees centigrade characteristic, then the current is reducing. Okay. So in this way, you see that there is an effect of temperature on the characteristic of the diode, which you don't normally see in the case of a conductor. Okay, you see the effect of temperature in a conductor when unless and until it becomes the temperature changes drastically. Okay, so usually we say that the current in a conductor is nearly constant, okay, irrespective of the temperature. So temperature is not taken into consideration unless and until we are operating the conductor at a reasonable temperature. You don't worry about the effect of temperature. But in the case of a diode, the effect of temperature, in the case of a semiconductor, the effect of temperature is significant. So these are the various, as I said, the 13 voltages. Germanium it is 0.3, silicon it is 0.7, gallium arsenide is 1.2,